So we're going to look at applying that continuous growth or exponential growth formula to continuous growth situations, and also looking at this new model called the logistic growth. I don't think you've seen that one before. I don't think it's covered in Algebra 2. All right, so our exponential growth and decay models. The formula looks a little different, but it's really just our PERT formula. Okay? It has the E in there, so it's a continuous growth kind of thing. They are using slightly different variables. All right, so the capital A with the little subscript 0 means initial amount. Okay? It's just not necessarily money, so we don't call it principal. It's just our initial amount. Okay? We have the E in there just like we do in our PERT. All right, we use that when it's continuous. And then the KT part is kind of like the RT part that we've had before. Okay, so your K value is like what R used to be. Again, it's just being a little more generic, so it's not necessarily tied to money. Okay. First example. Oops, I've missed something here. If K is positive, we have a growth situation. If K is negative, we have a decay situation. All right. In 2000, the population of Africa was 807 million, and by 2011, it had grown to 152 million. Now, they left it that way so that everything was in millions, okay, which means we don't need all the extra zeros in there. Find the exponential growth function that models this. Assume it's continuous growth. Okay, so let's plug in what we know. Do we know a final amount? What did they give us for the final amount? Okay. So final amount equals our initial amount, which was 807. And again, we don't have to put all the zeros since both of those numbers are in millions. All right, as long as they're the same units, we can leave that off. Then we need e to the kt power. K is kind of like what R used to be. Okay, but they haven't given us that, have they? They did give us some information about time, though. What do we know? 11 years. So our power here is K times 11. Okay, so what would we do first? How could we start solving this? Okay, so grab your calculators. Again, we're going to have some long decimals in there. I want you to keep that in your calculator. I have some on my desk if you need one. You're going to take 1052 and divide by 807. Okay, we'll have a decimal for that. Then what do we do? It's around 1.3. Everybody getting that? So we have a number about 1.3 equals e to the 11k. What would we do next? We could take natural log of both sides. So we want the natural log of that decimal that we just had. Okay, so take the natural log of that answer. Should get something like 0.265. Okay, and then what would we need to do? Divide it by 11. Okay, so what we are finding is our K value. K is 0.0241. Okay. So the question says to find an exponential growth function that models this situation. We now know K. We didn't know it at the beginning. So now we can kind of write a generic equation. Our final amount is going to be 807 e to the 0.0241 t. Okay, so we found K, so we can dump that into our formula, And now it's a little more generic. If we know a time, we can plug it in and find our total amount. If we know a total amount, we can work back and figure out our time. Okay. Part B says, when will Africa exceed 2,000 million? Which really means 2 billion people. But again, they're keeping it in terms of millions, so we don't have to put all those extra zeros. Everything's in millions. So where would we plug the 2,000? Where would that go in this formula here? Again, the question is, when will it exceed 2,000? Yeah, that's going where the f of t was. Okay, so we're going to put 2,000 in there. All right, and then what do we do to solve for t? Talk through the steps. What are we going to do? Divide by the 807, take the natural log, and then divide by k, right? Same steps we just did in the previous one. So we're going to take 2,000 divided by 807. We're going to take the natural log of that. And then once we get that answer, we can divide out that decimal. All right, so what do we end up with for t? I got 37.659. Yes? Okay, now it just says when. We need a year. So it's about a little over 37.5 years. From when? From 2000. So we are looking at 2037, partway into that year, that this would happen. Yes? Okay. We're going to skip the second example because it's the same thing we just did. Okay, are you guys okay with those steps? I do want to reiterate, in that first part, we are plugging in what we're given so we can find k, and then we go back to the more generic formula that would work for any time. Okay, now that we know the type of growth that's happening. All right. Second kind of growth model that we're going to look at today is called logistic growth. Okay, has a more complicated looking equation. It says A equals C divided by 1 plus AE to the negative BT. Okay, lots of pieces in there. Logistic growth is different from exponential growth. Exponential growth means it kind of starts gradually and then starts picking up, right? And then it just keeps going faster and faster. But there's a lot of things in life that can't continue to grow that way. All right? Population can grow, but eventually you're going to run out of space, or you're going to run out of enough food to maintain that growth. Okay? So there's a lot of things, plants. All right? Plants grow, but eventually they get to a point where they can't continue to grow and support themselves. Right? So the growth continues, but at a slower pace. In a logistic growth model, it starts out looking kind of like your exponential growth. All right, it's kind of flat at the beginning and then it starts curving up. It's going to hit a point where it's changing the growth pattern. It's still continuing to increase, but at a slower and slower pace. So it's increasing fast here in the green section, but then in the blue section, it's growing, but it's starting to slow down and level off again. Okay? So initial amount would be right there. Okay? Your initial amount would be your y-intercept. Okay? You have increasing growth right in here in that green section. And then we have a decreasing rate of growth. Now, I do want to point out, it is continuing to grow. All right? It's not decaying. It's just going slower. All right? It's slowing down in its growth process. And then we have something called the limit to growth. what is the maximum that that environment can support in terms of the population, or how tall can the plant grow before it starts tipping over, that kind of thing. So there is a limit to growth, and that is our top horizontal asymptote. We also have a horizontal asymptote at the x-axis. Okay, so in a logistic growth curve, you're going to have two horizontal asymptotes, and it's going to level off at the end for each of those. Okay, so we call that the limit to growth, and that is the C value in our equation. Okay, so looking back at the basic formula I gave you at the beginning, that top number, that C value, is the maximum. It's the limit that that can sustain. Okay? All right, so our first example here, our formula says f of t equals 30,000 divided by 1 plus 20 e to the negative 1.5 t. All right, it's a logistic growth. It says it models the number of people who have become ill with the influenza t weeks after the initial outbreak. So again, illnesses like that are follow a logistic growth type pattern very closely. So a few people are sick, pretty soon everybody starts to get sick, right? And then it kind of dies off. Does that make sense? Okay. So how many people were ill when the epidemic began? Well, what would the time be when it began? 0 times 0, right? Your starting amount. So we're going to put a 0 in for t. So in my formula, I'm looking for f of 0. We have 30,000 divided by 1 plus 20 e to the negative 1.5 times 0. Well, what's negative 1.5 times 0? What is e to the 0? It is 1. And a lot of students get confused and they say this whole 20 e to the power piece disappears. That's not correct. The e to the 0 part right here becomes a 1. And 20 times 1 is 20, plus the other one that's in the denominator makes it 21. So we're really looking at 30,000 divided by 21. Grab your calculators, figure that out. What do we get? What'd you get? Okay, he said 1428.57. Now, we're talking about people here, right? So we would round up to a whole number. So we're looking at about 1,429 people. Okay. How many people were ill after 4 weeks? Now go back and look. What did they define T to be? Is T in weeks? Okay. So we are going to just put a 4 in for T. So we have 30,000. We're dividing by 1 plus 20 e to the negative 1.5 times 4. Okay. Make sure that you are putting that whole denominator in parentheses, so it divides by all of that chunk. All right. Go ahead and calculate that. What are we getting? What'd you get? I had like 28,000 something. 28. 582? Okay, so 583? Okay, so when they first said there was an epidemic, all right, there were about 1,400 people ill. 4 weeks later, there's 28,000 people ill. Okay, so rapid growth, all right. Part C says, what is the highest number of people that can become sick according to this model? That's that limit to growth. Some people, some books call it a carrying capacity. Okay, different terms for it. But it's that maximum that we can get to, that top horizontal asymptote on my graph. So based on our equation, what is that? That's the 30,000. It's that C value, the numerator. Okay, so we are almost, after 4 weeks, to that maximum. All right, it's grown fast. It started to slow down. Now we're reaching that 30,000 mark. Okay. It says, when will the number infected reach 10,000? Well, it took us 4 weeks to get to 28,500. All right, so we know our answer has to be less than 4. So let's work backwards. We want our total to be 10,000. Our formula says we have 30,000 divided by 1 plus 20e to the negative 1.5t. So we're going to try to solve for t. Now this one's a little different because the variable we're solving for is in the denominator. We can't leave it there. So can you picture your first step in solving this is to take this denominator and multiply it over to that side? And then can we take the 10,000 that's over there and divide it to the other side? So can we do that in one step? Can you visualize that? Okay, so the denominator here is going to move up to the left side. The 10,000 is going to get divided down to the other side. Okay? So we have 1 plus 20e to the negative 1.5t equaling 30,000 divided by 10,000, which is just 3. Yes? Okay. What would we do next if we were trying to solve for t? Okay, let's get rid of the 1. So now we've got 20e to the negative 1.5t equals 2. Okay. Can we divide out the 20? All right, so we're going to have e to the negative 1.5t equals 2 divided by 20 would be 1/10. Okay. Can we take the natural log of both sides? So we have negative 1.5t equaling the natural log of 0.1. All right, so let's find the natural log of 0.1. And then we need to take that and divide by negative 1.5. So what does that mean? What are we getting? That's how many weeks? So about 1.5 weeks from when the epidemic started that we'd have 10,000 people ill? All right, questions on that process? Okay, the last one I'm going to have you try in your group, so I'm going to pause the video here. You've got 2 questions. Find the proportion of correct responses prior to learning trials beginning. So what is your starting amount? And then what is the limiting size of your function as trials continue? All right, go ahead and set it up as a group. So for parts A, we are looking for the proportion of correct responses prior to them doing learning trials. In other words, initially, how many people could successfully do it? Okay, whatever it is that they're learning here. So we are looking at what is the proportion at time 0. We have 0.8 divided by 1 plus d to the negative 2t, and we said t is 0. So what's negative 0.2 times 0? That's e to the 0, right? And e to the 0 is 1. So 1 plus 1 on the bottom, we have 0.8 divided by 2. Okay, so 0.4 is the proportion of correct responses before they start trying to teach it to you. Okay. What is the limiting size if they're continuing the trials? Based on our equation, what's the limit to growth? The 0.8, right? It's that top number. Okay. In a logistic growth model, that top value, that numerator, is your limit to growth, the maximum that could happen. So they're saying whatever this is that we're trying to learn, that even with practice, only 80% of the people are going to be able to do it. Okay? I added a question here. When would the proportion of correct responses be 0.6? Doesn't tell us. It's how many trials they do. Okay? So after how many trials would the proportion of correct responses be 0.6? Okay? So what are we going to have to do? Put 0.6 in for F. What was the equation? Negative something. Negative 0.2t. All right. So once again, can you picture taking that denominator and multiplying it over to the left? And taking what's on the left and dividing it over to the right? Okay. So we have 1 plus e to the negative 0.2t equaling 0.8 divided by 0.6. Well, what is that? It's the same as 8 over 6, which would be 4 over 3. 4/3? 1 1/3? Okay, so get that number on our calculator. What's our next step? Subtract the 1. So we have e to the negative 0.2t being 1/3. Okay, then what? Take the natural log of both sides. So negative 0.2t equals the natural log of 1/3. Then divide out your negative 0.2. All right, so natural log of 1/3. And then we're dividing by negative 0.2. Okay, so we have t being about 5.5. Yes? Okay. Questions on the logistic model? What's the top number in your formula represent? Your limit to growth. When you go to find the initial amount, remember that this whole piece here doesn't disappear, that e to the 0 becomes a 1, right? Okay. So you do have a book assignment today. You're doing 1 through 6, 8 through 14, 32, and 37 through 46.